Hello everyone, thanks for coming. Today we are going to do a review of our numerical analysis week 11's lectures. So in this week, we talk about composite integration formula as well as function approximations. So for the composite integration formula, we are breaking a long interval into many subintervals and then apply the numerical integration formula for each subinterval. We let xi to be a plus I times b minus a divided by m to be the grid point. The composite mid-trapezoidal rule is to use the trapezoidal rule for the integration of f over each subinterval and then sum them up. The Simpson's rule is to use the Simpson's formula for the for calculating the numerical integration in each subinterval and then sum them up. So finally, the midpoint rule is to use the midpoint formula to approximate the integration of f over each subinterval and them. So that's the composite integration formula. So similarly, we also have error estimate for the composite integration formulas. So let's suppose m2 is maximum of the absolute value of the second order derivative of f, and m4 is the maximum of the absolute value of the fourth order derivative of f. So for the composite trapezoidal rule, the error bound will be m2 over 12 times b minus a cubic divided by m squared. That is to say, the composite trapezoidal rule will converge at a rate of big O m squared, a quadratic rate with respect to the number of grids. The error estimate for the composite Simpson's rule will be m4 divided by 2880 times b minus a to the power 5 over m4. So the convergence rate of the composite Simpson's rule is big O m to the power 4. So we can see that the composite Simpson's rule could converge faster than the trapezoidal rule. Finally, for the composite midpoint rule, the convergence, the error bound will be m2 over 24 times b minus a cubic over m squared. So the convergence rate of the composite midpoint rule is the same as the convergence rate of the composite trapezoidal rule. So finally, we introduce the inner product space. It's another way of approximating a function by minimizing the two norm of the residual. So first, what is an inner product space? Let V be a linear space if we can define a real valued function on it such that the inputs, the entries are two elements in V, and it satisfies the linearity condition, that is f plus gh equals to fh plus gh, the homogeneity condition lambda f g equals to lambda times fg, interchangeability fg equals to gf, as a non-negativity f is greater than 0 if f is non-zero. Then we call this function a linear inner product, and we call this linear space with the inner product the inner product space. So here are some properties for the inner product. Orthogonality, that is to say, if the inner product of two elements f and g is 0, then we call those two elements are orthogonal to each other. Cauchy inequality, the inner product of f times the inner product of g is greater or equal than the inner square of the inner product of f and g. We can also define the induced norm. The norm of f is defined as the square root of the inner product of f and f. Finally, with the definition of the inner product space, we can get the best two norm approximation to a given function. Suppose fi forms a set of orthonormal basis functions, that is, the inner product of fi and fj equals to 0 if I does not equal to j, and equals to 1 if I equals to j. If Pn of x in the space spanned by the first n plus 1 basis functions minimizes the quantity, the norm of Gn minus Pn of x for all elements in the space capital Pn of x, then the coefficients Ci can be determined as the inner product of G of x and Fi of x. Thanks for listening.